integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. And more generally, if you're doing some u substitution, if you end up with the integral of my bottom button here. Sorry, I mean it's not a huge deal, but there. Okay. 1 over u du, or the integral of du over u is equal to the natural log of the absolute value of u. And so there are a lot of quote unquote easy log integrals that we can do in our head with practice. For example, the integral of say 1 over x plus 6 dx. You could do this the long way, right? You could totally say, I'm going to let u equal x plus 6. Du is going to equal 1 dx. And then replace this, rewrite this as the integral of 1 over u du. That u does not look good. And then that would be the natural log of the absolute value of u plus c, which would then be the natural log of the absolute value of x plus 6 plus c. Or you could be like, hey, I know that if my function is the natural log of x plus 4, I know the derivative of that is 1 over the stuff times the derivative of the stuff, but the derivative of x plus 4 is just 1. Well, if the derivative of a function is the thing I'm trying, oh, sorry, I did 4 instead of 6, apologies. Sorry, I meant to do 6. Right? If the derivative of this is equal to this, then the antiderivative of this is equal to this. But of course, I have to have absolute values around that. That's the only difference there is you need absolute values. So the point I'm trying to make here is that if you know something's derivative is what you've got, you know the antiderivative, so you don't have to do a u substitution. Where did my pen? Oh, right here. Similarly, right, we can even do it if we have something like, if I have, say, the integral of 1 over 3x plus 5. We could do this the long way and say u is going to equal 3x plus 5, du is going to be 3 dx, 1/3 du equals dx. So our integral is equal to 1/3 the integral of 1 over u du. And then we integrate that. We get the natural log of the absolute value of u plus c. We get 1/3 the natural log of the absolute value of 3x plus 5. Or we can do it the shorter way. We can say, well, I know that the derivative of the natural log of 3x plus 5 is 1 over 3x plus 5 times 3. And so then what we can do is we can be, well, like, I know that if I'm going to integrate this, so if I integrate this, I'm going to get that. So, but I really just want to integrate 1 over 3x plus 5. So the integral of this should be the natural log of the absolute value of 3x plus 5. And then I'm going to divide by 3 to account for the 3 I would have multiplied by using the chain rule. So this works for really anything, right? You could do it for the very, very general integral of 1 over ax plus b. We could say, well, I know that the derivative of the natural log of ax plus b is 1 over ax plus b times the derivative of ax plus b, which is just a. So if the derivative makes you multiply by a constant, the antiderivative is going to make you divide by that constant. So we're going to get 1 over a times the natural log of the absolute value of ax plus b. Let's see. So that's a rule you can remember for integrating 1 over something times x plus a constant. It always works. So if we want to integrate, say, the integral of 1 over 7 minus 5x dx, I know that's going to be the natural log of the opposite value of 7 minus 5x divided by what? Well, divided by -5. And you can write it as divided by -5 like that. But it's usually more standard to write it as times -1/5. So I would encourage you to write it that way, but either way, technically it's correct. Or we could do, right, and this is going to get old fast, right? We could do, say, like the integral of 6 over 17x plus 4. Well, we can bring the 6 out in front and say that's 6 times the integral of 1 over 17x plus 4 dx. And then we know that the integral of 1 over mx plus b or ax plus b is the natural log of the opposite value of 17x plus 4. But then I also have to multiply by a 1/17. And I would probably rewrite this as 6/17 natural log of 17x plus 4. So I could go on, but I feel like most of the examples are going to be pretty much the same, right? But let's do one that's a little bit different. So what if we had something more like this? The integral of, say, 1 over 4x plus 3 quantity squared. So here's what I really have to stress. This is not going to be the natural log, the log, right? It's not going to be the natural log of 4x plus 3 squared. Because the derivative of this is just going to be, well, in fact, you could bring down the 2 if you wanted to, but let's not. It would be 1 over 4x plus 3 squared times the derivative of 4x plus 3 squared, which is 2 times 4x plus 3 to the first times 4. And this cancels with that, and you get 8 over 4x plus 3, which is definitely not equal to that. So the antiderivative of this is not this, because the derivative of this is not that. And what I'm really trying to emphasize here is that you basically only get your antiderivative being a logarithmic thing if you've got 1 over something that is a linear thing, meaning x to the first power and no higher power or different power, really. So since I've got something, right, I've got like an x squared here, I have something different. So here I really do need to do the u substitution. So I'm going to say, all right, let's let u equal the stuff inside this part being squared. And then my du is equal to 4 times dx. So 1/4 du is equal to dx. And then I can rewrite my integral as, so let's see, the dx becomes 1/4 du. And then the 1 over 4x plus 3 squared becomes 1 over u squared, which I'm going to write as u to the -2nd. And then we're going to use our antiderivative rule. So we're going to do, let's be 1/4 u to the -1st divided by -1 plus c. So then divided by -1, let's just make that a -1/4 out in front. So that's going to be -1/4 times u to the -1st, which is 4x plus 3 to the -1st. And you can leave it like that, or I would probably opt to rewrite it as -1 over 4 times 4x plus 3 plus c. And I suppose you could even distribute the 4 on the bottom if you really wanted to. You get -1 over 16x plus 12. I don't need to, but you could. There are a few other things. Yeah. So another thing kind of that I have noticed over the years is that if you integrate something like this, you do the integral of, say, the derivative of a function divided by that function, you're going to get the natural log of that function in absolute value. Because what's the derivative of the natural log of a function? It's 1 over the function times the derivative of the function. That's exactly that. So when I see something like this, x plus 4 over x squared plus 8x plus 1, I'm thinking to myself, well, it looks like that bottom part, it looks like the derivative of that is essentially the top. Maybe we're off by a factor. Let's do the substitution and see. So u is going to be x squared plus 8x plus 1. Your du is going to be 2x plus 8 dx, which is exactly 2 times x plus 4 dx. So 1/2 du is equal to x plus 4 dx. And we exactly have 1/2 du over u. Du over u is just another way of saying f prime over f, right? It's the derivative of the thing divided by the thing. It's the derivative of the thing divided by the thing. The integral of that's going to be natural log of the absolute value of u, which is going to equal natural log of the absolute value of x squared plus 8x plus 1. Questions about anything I've done so far? You guys are like, no, we've seen this all. It's pretty straightforward. Or not. Maybe you have lots of questions. You're really welcome to ask them. By the way, just so I imagine you guys all know this, but just in case you don't, you always have the option to send me a private chat if you don't want anyone else to see your question. I'm usually mostly good about not saying so-and-so has asked me to do this. I'm going to say someone has asked. I don't mean to call anyone out if they've sent me a private message. Occasionally I have said someone's name accidentally because it's been a really good question. So try not to say your name if you send me a private message. But yeah, just that's all. I'll do my best. Let's look though at what happens if you take the reciprocal of this. Meaning, what if I wanted to do the integral of x squared plus 8x plus 1 divided by x plus 4? Well, now it doesn't work to do the same substitution, right? If you let u equal x squared plus 8x plus 1, your du is 2 times x plus 4 dx, but I don't have an x plus 4 times dx. I have a 1 over x plus 4 times dx. And letting u equal x plus 4 doesn't seem like it's going to get me anywhere either. So here's kind of the thing. This is always something that's worthwhile. If you have a rational function like this, where the degree on top is greater than or equal to the degree on the bottom, which is called an improper rational function, right? If you're right, just like 6/5 is an improper fraction because the numerator is larger than the denominator. X squared plus 8x plus 1 over x plus 4 is an improper rational function because the degree on top is greater than or equal to the degree on the bottom. But if that's the case, we do polynomial division. So I probably don't have quite enough room here. Let me do the polynomial division up here. So we're going to do x squared plus 8x plus 1 divided by x plus 4. So the way we do this, I hope all of you have seen this before. If you haven't, that's okay. I'm going to show you how to do it. Just like regular division, you're asking yourself, like if you're doing regular division, let's say you're doing, like, I don't know, 17 into 437. You ask yourself, what do you multiply by 17 to get 4? Oh, well, 0, right? You can't get 4 from 50. What do you multiply by 17 to get up to 43? I think 3 is too much, right? 3 times 17 is 51. So 2. 2 times 17 is 34. Then you subtract. 43 minus 34 is 9. You bring down the 7. And then you repeat the process. You say, what do you multiply by 17 to get up to 97, but not bigger than 97? And the answer is probably 4. Maybe 5. Yeah, I think 5. 5 times 17 is 85. 97 minus 85 is 12. So 437 divided by 17 would equal 25. And the remainder would be 12. So plus 12/17. That's how that works. going to work the same over here. Well, so the kind of small difference is that you look at the highest term, the highest power. So you ask yourself, what do you multiply by x to get x squared? And the answer is x. So then you multiply x by all of this. So x times x is x squared. X times plus 4 is plus 4x. And then we subtract. X squared minus x squared is 0. 8x minus 4x is 4x. Bring down the next thing and repeat the process. What do you multiply by x to get 4x? Oh, you multiply it by 4. 4 times x is 4x. 4 times 4 is 16. We subtract. And 1 minus, so 4x, the first part's always going to be 0. 1 minus 16 is negative 15. So that means we can rewrite this fraction, x squared plus 8x plus 1 over x plus 4. We can write that as the quotient x plus 4 plus the remainder divided by the divisor. It's a little bit, I feel like this example might not be excellent because the quotient and the divisor happen to end up being the same. We'll do another one where they're not, just to kind of really find the difference. But that's always what you get when you divide a rational function out, where the degree on top is bigger than or equal to the degree on the bottom. You get some result, some quotient, plus the remainder divided by the thing you're dividing by. Just like over here, right? 437 divided by 17 is the quotient 25 plus the remainder divided by the thing you're dividing by. And then we can integrate that. The antiderivative of x is x squared over 2. The antiderivative of 4 is 4x. And the antiderivative of negative 15 over x plus 4 is minus 15 times the natural log of the absolute value of x plus 4 plus c. Questions here? It's super quiet today. I mean, that's all right, but I feel like usually there's a little bit more chatter, engagement. I know it's a little, 9 o'clock's a little early. Not really, but I mean, it is. It is depending on who you are. It's not early for me. I was awake at 4:30 this morning, which is too early. I usually try to shoot for more like 5:30, but sometimes you just wake up. All right, let's look at another example. Yeah, let's not do that one. Let's just I'm going to make one up. Let's say we want to do something like the integral of, sure, 2x cubed plus 5x squared minus 6x plus 9 divided by, I don't know. Let's make it not that. Don't be silly, James. Let's make it x plus 3. So clearly here, oh, thank you. Chem exams. Chem is hard. Definitely good luck with the chem if you have one. If you already had one, I hope it went well. If you have one soon, best of luck. If you have one soon, you're welcome to leave class and study for it if that is what you need to spend your time doing, right? You certainly, everyone who's been here already has been here long enough to get counted. But right, definitely priorities, right? I know this is important, but I know your chem exam might be a little bit more important. So totally understand if you need to do that, or mute me and study for your chem exam while you're still here. That's also fine. All right, so same process. I'm going to do the division, x plus 3 into 2x cubed plus 5x squared minus 6x plus 9. Just some terminology in case you didn't catch it the first time. When you have a fraction, the top part is called the dividend. The bottom part is called the divisor. The part we get up here is called the quotient, or the answer, result. And then the remaining part down here is the remainder. So when you multiply by x to get 2x cubed, 2x squared. 2x squared times x is 2x cubed. 2x squared times 3 is 6x squared. Subtract. This minus this is always going to be 0. This minus this is going to be minus x squared. Some people do a thing where they like change the signs. I don't like to do that. I like to just put parentheses around it and say it's subtraction. Bring down the next term. x times negative x will give me negative x squared. Negative x times x is negative x squared. Negative x times 3 is negative 3x. Subtract. Negative x squared minus negative x squared is 0. Negative 6x minus negative 3x is negative 6x plus 3x, which is negative 3x. And I was worried I came up with one that was not going to have a remainder, but it does. It's close though. So when you multiply by x to get negative 3x, it's negative 3. Negative 3 times negative x times x is negative 3x. Negative 3 times 3 is negative 9. Subtract. This minus this is 0 because they're the same. 9 minus negative 9 is 9 plus 9, which is 18. So we can rewrite this integral as the integral of the quotient 2x squared minus x minus 3 plus the remainder divided by the divisor. And now we can integrate that. So that's going to be, let's see, 2x, that's fine. 2x cubed over 3 minus x squared over 2 minus 3x plus 18 natural log of the absolute value of x plus 3 plus c. Yeah. So definitely if the degree on top is, and we'll do one more example, if the degree on top is greater than or equal to the degree on the bottom, you have to use, you don't always absolutely have to, but most of the time you have to do polynomial division. There are a couple of exceptions to that. In fact, this next example is an exception. So I'll show you this one 2 different ways. So can we do a couple more? Yeah, sure, of course, Lauren. Let's do, I've got this one, and we can do another one as well. So this one's actually pretty easy. If you want to do it. So I will say, yes, we can, but we're kind of limited. And the reason we're limited is because we're limited in what our denominator can actually be. Right? We don't really have the tools yet for dealing with more complicated denominators other than the denominator that's like just x to the first plus or minus something. But later on, we will talk about how to do partial fractions, and that'll kind of open up the possibilities for what we can do. But that's not yet. So it's going to be in a little while. We'll definitely revisit this later. Let's do a couple more. So for this one, you could do this one using polynomial division. And in fact, this one is really easy with polynomial division. X plus 3 divided by x minus 1. And we can use it because the degree on top is bigger than or equal to the degree on the bottom. The degree on top is 1. The degree on the bottom is also 1. When you multiply by x to get x, you multiply by 1. 1 times x minus 1 is x minus 1. Subtract. X minus x is 0. 3 minus 1 is 4. So this is equal to the integral of 1 plus 4 over x minus 1. And then we would get x plus 4 times the natural log of the absolute value of x minus 1. Sometimes when the degree on top and the degree on the bottom are the same, people do this kind of tricky thing where they're like, well, I can just do this. I can be like, well, I can make the top, instead of being x plus 3, I can say the top is x minus 1 plus 4. Still the same as it was before, I just wrote it differently. And then you can break it up as x minus 1 over x minus 1 plus 4 over x minus 1. And then x minus 1 over x minus 1 is 1. So you get to that. That's a tricky way some people do ones like this, where it's like, oh, I can see that the top and the bottom are pretty much the same. Let's just make the top the same and then adjust. The other way people do this one, which is very different, is using a u substitution and a back substitution, which I don't think we've talked about. That's where you would say, I'm going to let u equal the denominator. And then du is going to be dx. So then when I start rewriting this, I get, well, let's see. The denominator is u, dx is du. And then the top, I still have an x left. So what I'm going to do with that x plus 3, well, I'm going to do what's called a back substitution, where I'm going to solve this for x. u plus 1 is equal to x. So this is what's going to go in for x right there. So this is going to equal the integral of u plus 1 plus 3 over u. U plus 1 plus 3 is just u plus 4. In fact, really I should say u divided by u is just 1, and 4 divided by u is 4 over u. So now we integrate this, and we get u. Oh, sorry, I'm still writing dx. I should be writing du. That's terrible. Apologies. So the integral of 1 is u, and the integral of 4 over u is 4 natural log of the absolute value of u. And so then, if we rewrite our answer, right, if we plug back in what x is, what u is x minus 1, we get x minus 1 plus 4 times the natural log of the absolute value of x minus 1 plus c. And I want to point out, because this is kind of interesting, we used a different method, and we got an answer that differed by a constant. Right? Doing it this way, we did the polynomial division. Our answer was x plus 4 natural log of x minus 1 plus c. Doing it this way, our answer was x minus 1 plus 4 natural log of x minus 1 plus c. So a slightly different answer, still a valid answer, right? As long as your answers are the same up to a constant, it's perfectly fine. But I just want to really kind of remark there, if you use a different method of integration sometimes, which you don't usually have the option to, but occasionally you will, you can get a slightly different answer. Let's do another one. And then we will, and then I think, oh, and then I've got one other kind of super funky one, and then we will move along. Not that one. A couple funky ones. Yeah, okay, sure. So I'm going to make one up, and the numbers might not come out to be super nice. It's okay, sometimes it happens. Let's say we have the integral of, let's say 6x cubed plus, plus 5x minus 7 over 2x minus 1. Okay, so let's do the polynomial division again. This one's going to have kind of an extra little bit. So I'm getting this divided by that. So 2x minus 1 is the divisor. We're dividing into 6x cubed. And since there isn't an x squared term, I'm going to write 0x squared plus 5x minus 7. So if you're ever missing any of the in-between powers of x, just write them in as 0 times x squared over that power is. What do you multiply by 2x to get 6x cubed? It's going to be 3x squared. 3x squared times 2x is 6x cubed. 3x squared times minus 1 is minus 3x squared. Subtract. And let's see. And this is, so things are going to get a little bit hairy here. That's okay. This minus this is 0. This minus this is going to be plus 3x squared. Bring down the 5x. Okay, so now the numbers are going to get not very nice. So I didn't turn this one ahead. What do you multiply by 2x to get 3x squared? It's going to be 3 halves x. 3 halves x times 2 is going to be 3x squared. And 3 halves x times 1 is going to be minus 3 halves x. Okay, we subtract. 3x squared minus 3x squared is 0. 5x plus 3 halves. So 5 plus 3 halves is 10 halves plus 3 halves, which is 13 halves. Okay, what do you multiply by 2 to get 13 halves? 2 times what equals 13 halves? We'll divide both sides by 2, and you get 13 fourths. So you're going to have 13 fourths up here, right? Usually the people writing these problems have done a better job of planning them out. They don't get quite that gnarly numbers here. But 13 fourths times 2 is 13 halves x. And 13 fourths times negative 1 is minus 13 fourths. And I'm running out of room. So if we do the subtraction here, we get 0 and we get minus 7 plus 13 fourths. So minus 7 plus 13 fourths is minus 28 fourths. plus 13/4, which is negative 15/4. So, I'm out of room. I guess I can write it on the other side. So I've had the integral of 6x equals 5x minus 7 over 2x minus 1 dx, and then it's equal to the integral of our quotient, 3x squared plus 3 halves x plus 13/4, plus our remainder, which is negative 15/4, divided by our divisor, which is 2x minus 1. So I'm going to write that as minus 15/4 over 2x minus 1. Okay, now we can integrate. So we're going to get x cubed, or 3x cubed over 3, plus 3 halves x squared over 2, or 3/4 x squared, plus 13/4 x. And then here, we're going to get minus 15/4, right? Because really, I'm thinking of this as minus 15/4 times 1 over 2x minus 1. So the constant multiple just sticks around, and the integral of 1 over 2x minus 1 is going to be the natural log of the absolute value of 2x minus 1 divided by 2, or multiplied by 1/2. So that's how I would do that problem. Let's do a couple E1s, and then we will move on to section 5.4. So let me remind you, when do we use polynomial division? When the degree on top is bigger than or equal to the degree on the bottom. Later on, we'll see how to deal with something like this. The integral of x cubed over, say, x squared plus 1. The issue with something like this is you have to know how to integrate 1 over x squared plus 1 before you can deal with this. So we're not there yet. We might, now that I said it, we might not actually get there. That might be an integral that we actually don't talk about in this class, but we will certainly visit things like it, if not that one. We can do x cubed over x squared minus 1 for sure. So let's look at these next couple problems. Let's say I have the integral of e to the 1 over x cubed over x to the 4th. So I'm not exactly sure here, but it looks like it would make sense to probably try letting u equal 1 over x cubed. And you could also try letting u equal x to the 4th. Right, both of those seem like good candidates, right? 1 over x cubed is in the exponent here, x to the 4th is in the denominator. One of those is going to work out, one of them isn't. The x to the 4th is not. Because if you let u equal x to the 4th, your du is 4x cubed dx, and we don't really have that. So instead, let's try letting u equal 1 over x cubed, which I would rather write as x to the negative 3rd. Then my du is negative 3 times x to the negative 3 minus 1. Which I do have an x to the negative 4th. It's just not written that way. So I can rewrite my integral as e to the 1 over x cubed times x to the negative 4th dx. Then if I divide both sides of this by negative 3, I get negative 1/3 du equal to, I forgot my dx here, sorry about that, equals x to the negative 4th dx. So then look, here is my negative 1/3 du, there's my u. So I can rewrite this integral as negative 1/3 integral du, right? I've taken care of all this. The other part left is the e to the u. And we know that the antiderivative of e to the u is e to the u. So I end up with negative 1/3 e to the x to the negative third, or 1 over x cubed if you prefer. Let's see. Okay, so there's a couple more examples. One of these is tricky, one of them is less tricky. And so as usual, I don't remember what I've said in this class. The tricky one, I'm not sure if we've seen this trick or not before, but let's do the not tricky one first. Let's do the integral of e to the 3x over 4 plus e to the 3x. In fact, I think that, I don't remember. It might have been your quiz. No, you guys didn't have a quiz last year. So here I would try letting u equal 4 plus e to the 3x. And my du is going to be e to the 3x times 3 dx. So then 1/3 du is equal to e to the 3x dx. Great, I've got that. So I can rewrite this integral as the integral of du over u. The integral of du over u for the 10th time today is the natural log of the absolute value of u plus c. And then this is equal to the natural log of the absolute value of 4 plus e to the 3x. One thing to note here, if you look like in the solutions manual, if you saw this problem in the textbook and the solutions manual, they would probably write the answer as the natural log of just 4 plus e to the 3x without the absolute values. And the reason they would get rid of them, oh, you're right, I did, no, thank you for the message. I totally forgot the 1/3. Good call, right? I should have had, my integral should have been not just du over u, right? Because this isn't equal to du. This is equal to 1/3 du. Thank you so much. So there should have been a 1/3 out in front, a 1/3 out in front, a 1/3 out in front. Good call. Thank you. Oh, gee, a pen all over my hands. It's just the worst. 1 second. Sorry. Luckily, saliva takes care of it pretty easily. Ugh. So do not love the whiteboard pens. Whatever, it's life as a teacher. So the reason that you don't need the absolute values in this particular problem is because 4 plus e to the 3x is already always positive. In fact, it's always greater than 4. So if you see something that happens to always be positive already, it is perfectly fine to drop the absolute values. You do not have to, though. So if you never want to think about it, you never have to think about it. Yeah. So just in case you see that in the textbook, like, why isn't there an absolute value? It's because the thing inside the absolute value is already always positive. A similar example is if you integrate 2x over x squared plus 1, for example. Here, I think we can all see that the top is exactly the derivative of the bottom. So we can see that, oh, that's going to be the natural log of the absolute value of x squared plus 1. I skipped doing the u substitution because it's like, hey, I know that if I let u equal the denominator, my derivative is exactly going to be 2x dx. So this would be the integral of du over u, which is the natural log of u, which is the natural log of the denominator. But then for a problem like this, someone also would say, well, I'm just going to write it without the absolute values because I know that x squared plus 1 is already always a positive number. So that's another example of it. One more of these. It's kind of tricky. And then we'll move on to talking about the fundamental theorem of calculus, which is what we use to find the area under curves, between curves, etc., etc. So let's look at this one. The integral of 1 over 2 plus e to the negative 3x dx. Does anyone have any suggestions as to what we might be able to do for this problem? I've got kind of 2 different ways to go here, and we'll talk about both. That's a good suggestion. I'm going to warn you, just because I know how this problem goes, it's actually not going to work out. But actually, that's a good point, Lauren, that while you could totally use sub for e to the negative 3x, it's most of the time, I would say almost always, if you can pick u equal to something or u equal to something plus a constant, it's almost always better to pick the plus the constant part, because your derivative is going to be the same either way, right? If you pick u equal to e to the negative 3x, your du would be e to the negative 3x times negative 3. But that would be the same way that you pick u equal to that, or you pick u equal to that, right? Same derivative either way. So if either one of these was the right choice, this one with the plus 2 would be the better choice. The issue here is that neither of these is the right choice. And the problem here is that if you, that's what I want to say. Yeah, the problem is I don't really have that, right? So there's a couple ways to do this one. One way we can do it, one thing we can try, which is not what I usually think of, is, yeah, but actually, so Elena, hopefully I'm saying your name right. You are on the right track. That's the way I just think about it. I'm going to show you guys that way. I'm also going to show you a different way. So here's one way of thinking about it. We could totally multiply the whole thing by e to the positive 3x. Specifically, you're looking to multiply by the thing that's the opposite sign of this thing. So you can multiply it by e to the 3x over e to the 3x. So then you get the integral of e to the 3x on top, and you get 2e to the 3x, and e to the 3x times e to the negative 3x is e to the 0, which is 1. And now we're going to make the choice to let u equal, well, actually the same kind of comments going to come back into play. We could pick 2e to the 3x, which would be fine. If you made this choice, you would get this being essentially du. You'd get du over u plus 1. And the integral of 1 over u plus 1 is the natural log of the absolute value of u plus 1. But we could also just sneak that one in there. And then the du is going to be the same either way, right? Either way, the derivative of this is going to be 2e to the 3x times 3, right? Also, I should mention, I've seen a few people in the quizzes make the mistake of taking the derivative of, say, e to the 3x and getting e to the 3x times 3x. It's not times all the stuff up here, it's times the derivative of all the stuff up there. So just be a little extra careful with those. So either, right, we're going to do it this way. And then I'm going to say, well, I have an e to the 3x dx. So I'm going to divide both sides of this by 6 and say 1/6 du equals e to the 3x dx. So my integral now is going to equal 1/6 integral of du and or 1 over u. I could have written du over u, right? So e to the 3x dx is my 1 times du. Sorry, I have 1/6 times 1 times du, and then the bottom is just u. And sorry, was someone saying something there? I thought I heard something, but maybe I'm just hearing. So then we get 1/6 natural log of the absolute value of u plus c, which is 1/6 the natural log of e to the 3x, sorry, 2e to the 3x. And this is my preferred way of doing this type of problem, but I do want to point out, it may not be super intuitive. You might be like, oh, I don't remember how to do the thing. There is another way to tackle this problem, which is actually going to give us a slightly different looking answer, which is okay. So here's another way of doing this problem. So when you have a problem and you don't know what to do with it, something you can try doing is just rewriting it. That's often a tactic we take. This one, where I have the integral of what was it again? 1 over 2 plus e to the negative 3x. One thing we could try doing is rewriting it as, oh, interesting. I'm looking at these notes here, and there's actually a slight error in the notes, which is fine. I'm going to fix it here, but yeah, maybe the answer is not going to look quite as different as I thought it was. So we can rewrite this as the integral of 1 over 2 plus 1 over e to the 3x. Okay, that's not looking great so far, but now let's maybe get a common denominator in the denominator. So I'm going to write this as 1 over 2e to the 3x over e to the 3x plus 1 over e to the 3x. And then I can combine those to get 2e to the 3x plus 1 over e to the 3x. And then when you've got something divided by a fraction, you can flip and multiply it. And you can write that as the integral of e to the 3x over 2e to the 3x plus 1. And we're definitely back to where we started here. So that's another way you can go about doing this one. I don't feel like I've seen this trick enough times to know that, oh, when you see something like this, you're not sure what to do. You can multiply the top and bottom by e to the opposite sign power here. But another way to go about it would be to say, well, I don't know what to do with that. Let's rewrite it. Let's get a common denominator. Let's put those fractions together. Let's flip and multiply. Oh, look, we got the same place. So many ways to tackle the same problem. So let's move along. Let's talk about area. Section 5.4 of your textbook. It's actually, like I said, I think I have an older version of it. I mean, it's not like I was supposed to change all that much of the version of it. But yeah, I have the 7th edition. I'm not sure what edition you guys are on. They're pretty much the same. So here is the notation we're going to use. The integral from a to b of f of x dx, meaning the net area under the curve f of x between a and b, is going to be equal to capital F of b minus capital F of a, where capital F is an antiderivative of little f. Okay, so let's look at an example. We want to find the area under the curve. What do I got here? F of x equal to 2x plus 1 from x equals 1 to x equals 3. I just want to point out, right? And when we write the integral, that's going to be our a value. That's going to be our b value. But we're not going to write the integral just yet. We're going to talk about the meaning behind this. So do I have enough room to draw? Let me draw my picture on the other side. So we're not going to get too into the details here, but we're going to get into enough of the details. So let's say here's my function 2x plus 1. And we're going from 1 to 3. Let's say there's 1, there's 3. So we are looking at this region here. And here's the idea. We are going to fill this region with very, very thin rectangles. And the area of all those rectangles added up together is going to be the area under the curve. So like we've got a little rectangle here, a little rectangle here, right? That's the whole idea, is we're just filling this up with rectangles. Okay, I can draw more rectangles, but I don't need to. So the thing I want to ask is, the thing I want to say is that an integral is just like kind of an adding machine. We just have to tell it what we want it to add up. In this case, we want it to add up all the rectangles. So here's what we're going to do. We're going to say the area is going to be the integral, right? And again, right, the integral means we're adding up. So the integral is we're adding up. We're adding up whatever's inside. So we want to add up all the areas of the rectangles. Okay, so the area of the rectangle, I don't have any area of the rectangle, it's height times the base. Easy enough. Okay, well, in this particular problem, what's the height of the rectangle? Well, the height of the rectangle is just whatever the function value is, right? So if I look at just one of these rectangles, right, here's let's take that rectangle. Sure, there's my rectangle. The height of this rectangle is just whatever the function is, which is 2x plus 1. Right? The height, I should say really, it's the height of the rectangle that's located at x. Right? We're saying go over x, the rectangle at x has a height of 2x minus 1. So if x is equal to 1, the height of the rectangle is 2 times 1 plus 1, which is 3. If x is equal to 2, the height of the rectangle is 4 plus 1, which is 5. If x is equal to 1.56, the height of the rectangle is 2 times 1.56 plus 1, right? This is just saying for any x value, the height of the rectangle at x is going to be 2x plus 1. And then the base of the rectangle, or the width of the rectangle, that's going to be a delta x, or a dx, a small change in x. So when I write this, the height is going to be 2x plus 1, and the base is going to be dx. I want to be super extra clear about the dx part, right? Dx just means a small change in x. And all of these rectangles, which are super thin, their base is a small change in x. Okay, then so we're adding up all the rectangles from as far left, well, the leftmost rectangle is at x equal to 1, and the rightmost rectangle is at x equal to 3. That's the whole story, right? Every rectangle has a height, that's the function height, and the base is gx, and then we're just adding them all up. Okay, so then we're going to do it. So the fundamental theorem of calculus tells us that we can find the area under a curve by doing the antiderivative of that function evaluated at the top limit minus the antiderivative evaluated at the bottom limit. So antidifferentiating 2x plus 1, we get x squared plus x. This is typical notation. We write a vertical line from 1 to 3, which just means you plug in the 3 first, minus you plug in the 1 second. Right? And this here, right, this is your capital F antiderivative of 3 minus your capital F antiderivative of 4. So then this ends up being 9 plus 3, which is 12, minus 1 plus 1, which is 2, so we get 10. And for this particular example, we can actually check, right? Because this shape, let me draw it again over here. This shape is just a trapezoid. And I could never tell you what the area of a trapezoid actually is. But I know that this is y equals 2x plus 1. I know this point here is 1 comma, let's see, if I plug in 1 for x, I get 2 plus 1, which is 3. If I plug in 3 for x, I get 6 plus 1, which is 7. So this trapezoid, I'm really thinking of as a rectangle plus a triangle. The area of this rectangle is, well, the base is 2 and the height is 3. 2 times 3 is 6. The area of this triangle, well, the base is 2 and the height is, the height from 3 to 7 is 4. So 2 times 4, but it's half of that. So 1/2 base times height is 1/2 2 times 4, which is just 4. And you add the areas together, oh, you get 10. So it checks out. There are questions about this example before we do more of these. Sorry, it's this. So this is our fundamental theorem of calculus. I will point out, technically this is the fundamental theorem of calculus part 2. There is a first part of the fundamental theorem of calculus that I don't think we're going to talk about in this class. But we've actually already talked about it. All the fundamental theorem of calculus part 1 says is that the derivative of the antiderivative is equal to the original function. Right. So if you take, say, the antiderivative of, I don't know, x cubed plus 1 dx, for example, it's kind of boring. Let's make it a little more interesting. Let's make x cubed plus cosine of x. Right, the antiderivative of that is equal to x to the 4th over 4 plus sine of x plus c. And then if you take the derivative of that, well, the derivative of x to the 4th over 4 is 4x cubed over 4. The derivative of sine x is cosine x. The derivative of c is 0. All the fundamental theorem of calculus says is that if you take the derivative of the antiderivative of a function, you get back the function. Seems pretty straightforward, right? We know this already, that the derivative and the antiderivative should undo what the other one does. Okay, so let's look at some more examples. One second. So let's find the area under f of x equal to 1 over x from x equals 1 to x equals e. Technically, there's no need to draw the function here, right? You could just say, oh, they're telling me to do a thing. It's going to be the integral from 1 to e of 1 over x dx. But I think it's worthwhile to draw a picture just so that we're really kind of making the connection between what they're asking us to do and what it's representing graphically. So here's the function 1 over x. At 1, it's equal to 1. And at e, there's 1, there's 2, there's 3, there's e. At e, it's equal to 1 over e. I don't really care. But so we are finding the area of this region here. And again, all we're doing is we're using little rectangles. So all this integral is saying is add up the area of these rectangles. Right? Each of those rectangles has a height of 1 over x and a base or a width, if you prefer, of dx. And they go as far left as x equal to 1, and they go as far right as x equal to e. I do think it is worth your mental energy to think of this when you're thinking about an integral. They are going to get more complicated and be less representative of these things later on. But for now, it's really going to be like, oh yeah, if we're doing a definite integral where you have limits of integration, it's representative of some sort of area. So here, we're going to get the antiderivative of 1 over x is the natural log of the absolute value of x. We don't need the plus c here, although you could have it. Let's say we put it in there just for fun, from 1 to e. When I plug in the e, I get the natural log of the absolute value of e plus c, minus when I plug in the 1, I get the natural log of the absolute value of 1 plus c. The c's cancel out, which is why we didn't need them in the first place. Someone's fire alarm is going off like 3 houses down. I hope Like I feel like maybe I should go look. Not gonna worry about it. Natural log of e is 1. Natural log of 1 is 0. So the area under this curve is actually equal to just 1. There was something. Okay, let's stop the graph. There's something else I wanted to say here. Oh, I know what it is. Okay. So I do want to emphasize the difference between a definite integral and an indefinite integral. So definite integral is like the two we just did. The defining characteristic that makes a definite integral definite is having limits of integration. So for example, the integral from, let's make it easy, let's say the integral from 0 to 4 of 3x squared dx. This integral would be, well, the antiderivative 3x squared is x cubed, evaluated between 0 and 4. It's always the top limit first. So it's going to be 4 cubed minus 0 cubed, which is 64. On the other hand, an indefinite integral does not have limits of integration. Indefinite integral. Doesn't matter how we spell it. Would be like this. And the answer would just be x cubed plus c. So here's the thing to remember. Definite integral has limits of integration. And when you find a definite integral, your answer is a number. So definite integrals, your answer is a number, typically representative of some sort of area under the curve. The reason why I don't say exactly that, sometimes it's like area between curves, sometimes it's area under a curve, it kind of depends. On the other hand, an indefinite integral, also known as an antiderivative, and the answer you get is not a number, the answer is a function. So that's the difference. Definite integrals, you're finding the area, your answer is a number. Indefinite integrals, also known as antiderivatives, you're just finding the antiderivative, which is a function. Definite integrals, you never need the plus c. Indefinite integrals, you do need the plus c. Unless there's an initial condition where then you solve for c. Okay, let's look at a few more examples of definite integrals. So let's evaluate the following. Let's evaluate the integral from 0 to 3 of x squared minus 9. Okay, so let's just calculate it and see what happens. So we're going to get, let's see, antiderivative of x squared is x cubed over 3. Antiderivative of 9 is 9x, 0 to 3. Plug in the 3 first, you get 3 cubed over 3 minus 9 times 3. Plug in the 0 second. A lot of the times, especially if things are x to a power, you're going to get just 0 when you plug in 0. So we get 0 here, minus 0 there. We didn't in the previous problem, which I think I already erased, right? The previous problem, we had an e to the 0, which is 1. So I just want to make sure that you understand, right? When you plug in 0, you don't always get 0, but a lot of the time you do. Let's see what we get here. So let's see, 3 cubed over 3 is 27 over 3, which is 9. Minus 9 times 3 is 27. That's negative 18. So why are we getting a negative answer? Well, it's because our region is actually below the x-axis. So if you look at this here, if you graph x squared minus 9, it looks like, right, this parabola. And we're specifically looking at this part right here. And so what's happening, right, if Right? If we're saying our height is y equals x squared minus 9, well, that means our height is negative, which is why we're getting a negative area there. So here's the thing. If you're told to just evaluate an integral and it comes out negative, perfectly fine. But if we want the area, we have to be careful about how we set it up. So if someone said, instead of this being the problem, if someone said, find the area between this curve, y equals x squared minus 9, and I could just say, find the area of this curve, find the area of y equal to x squared minus 9 in the fourth quadrant, which is this area here. Well, if you did this integral, that's actually not the right way to do it. You could just say, well, I know it's going to be that thing, just make it positive, which would totally be correct. But the right way to do this, if you want to find area and not just evaluate the integral, is to say, okay, well, the area is the integral of height times width. From 0 to 3. The width of this rectangle is still dx. The height of this rectangle is not quite x squared minus 9. The height, if you're trying to find the height of the rectangle, you want it to be a positive height. It should be the top of the rectangle minus the bottom of the rectangle. So the height of this rectangle would be 0 minus x squared minus 9. Which makes sense, right? If we're over here at 0, so when x is 0, this point is 0 minus negative 9, and the height, the height of this rectangle is 0 minus negative 9, which is 0 plus 9, which is 9. Oh, that's a positive number. So whenever you're finding the height of your rectangle and you're drawing something like this, you always want to think about it being the top thing minus the bottom thing. And sometimes your top is just 0. So then that's going to be the integral from 0 to 3 of negative x squared plus 9. And I think you guys can see that it's going to come out to be, it's going to come out to be the positive answer from what we had before because, right, we're just changing the sign of it. We can still show the work though. It's going to be negative x cubed over 3 plus 9x from 0 to 3. And if we plug in 3 now, we get negative 27 thirds plus 27 minus negative 0 plus 0. And that's going to be negative 9 plus 27, which is 18. So, some more. What if I wanted to evaluate, say, I'm going to do two different questions. I want to find, how do I want to phrase this? Yeah, I want to evaluate this integral from 0 to pi of cosine of x dx. But then I also want to find the area between f of x equal to cosine of x and the x-axis between x equals 0 and x equals pi. Okay, let's do the first one. Antiderivative cosine is positive sine from 0 to pi. So we get sine of pi minus sine of 0. Sine of pi is 0. Sine of 0 is 0. So the integral comes out to be 0. But there's not 0 area, right? We've seen the cosine function before, right? There's definitely more than there's more than a 0 amount of area. So here's what cosine looks like. So negative pi over 2, 0, pi over 2, pi, 3 pi over 2. So cosine of 0 is 1, and this kind of deal. So we're looking at this. So the problem is that from 0 to pi, which function is on top actually changes halfway through. So if you want to find the actual area between the two curves and not just the net area. So what this tells you is it's the net amount of area that's above the x-axis that's below the curve. The problem is the area that's above the x-axis totally cancels out with the area that's below the x-axis. So this is getting counted as positive, but this is getting counted as negative. And when you add them together, you get 0. So the long way of doing this one is to say, well, the actual area is going to be the integral from 0 to pi over 2 of your height is cosine x minus 0. Your width is dx plus the integral from pi over 2 to pi. Now your height is 0 minus cosine x. And your width is still dx. So the integral of cosine is sine. So you get sine of x from 0 to pi over 2. Plus integral of negative cosine is negative sine of x from pi over 2 to pi. Here we could have also just used the symmetry and said, I know that this region is the same as that, so they're going to just be the same and double it. But I'm not doing that. So sine of pi over 2 minus sine of 0 plus negative sine of pi minus negative sine of pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. Sine of pi is 0. Sine of pi over 2 is 1. So you end up with 1 minus 0 plus 0 plus 1, which is 2. So that's how much area is between these two curves. And we got time. We got time for one more. I want to find the area between what have I got here? Sorry. Y equals x squared minus 3x and y equal to x. So we don't need to graph it. I'm going to graph it. So y equals x squared minus 3x is y equals x times x minus 3. It's got x-intercepts at 0 and 3. The parabola does this kind of deal, sure. And then y equals x looks like that. So they have to intersect. They intersect here at 0, 0, and they also intersect over here at, let's see, they intersect if I set them equal to each other. Bring the x over here, x squared minus 4x equals 0, x times x minus 4 equals 0. So they intersect at 0 and at 4. This one here is 4, comma, if you plug in x equals 4, you get y equals 4. So I want to find all this area. So what I'm going to do is I'm going to use a rectangle again, right? I'm going to say, okay, my area, I'm going to add up all the things from as far left as x equals 0 to as far right as x equals 4 of the height of the rectangle times the width of the rectangle, or more generally, the area of the rectangle. So that's going to be the integral from 0 to 4. The height of the rectangle is the top function minus the bottom function. That's going to be x minus x squared minus 3x times the width, which is dx. Now I want to point out, if you graph it, it's easy to see which one's on top. But if you don't graph it, you have to kind of do something else. So let's pretend like we didn't graph it. How would you tell which of these functions was on top or bigger? Well, specifically, we're between the interval of x equal to 0 and x equal to 4. They intersect at 4 and at 0, but not anywhere else. So if you know which one's bigger at any point in between, you know which one's bigger the whole way. So I'm going to pick any number between where they intersect. Let's pick x equal to 2. If x is 2, then this function is going to equal 2, and this function is going to equal 4 minus 6, which is negative 2. Clearly, this is the larger one in the interval. So that's the one, y equals x, that's going to be the top. So if you're finding the area between curves, you get the integral from where they intersect to where they intersect of the top one minus the bottom one dx. And then we simplify. You get the integral from 0 to 4 of x minus 3x is 4x minus x squared. You antidifferentiate, you get 4x squared over 2, which is 2x squared, minus x cubed over 3 from 0 to 4. Plugging in the 4, you get 2 times 16. Plugging in the 4, you get minus 64 over 3. And that ends up being 96 over 3 minus 64 over 3, which is 32 over 3. Well, the birds are going crazy out there. All right, that's all I have for today.